Hello everybody, my name is Jerry Salen and the webinar today is Importance of Mixing for Heterogeneous Continuous Processes. A quick couple notes about our company. I'm the president of Nalis Engineering Services, and we like to say that we have solutions that scale because oftentimes chemistry does not scale directly up, and there's reasons for that. Is that there's a lot of engineering challenges that we're met with, including heat transfer, mass transfer, and today's topic, mixing. What we'd like to do is use a variety of tools, including in situ IR, Raman, focus beam reflectance measurement, particle vision microscopy tools, and also heat flow. We take our processes and we evaluate them at the pilot and in production equipment using models. And we also use a variety of scale down experiments, which we're going to talk about and discuss some of the successes of using that approach today. Overall, we like to develop sustainable and low-cost chemical processes for our customers. So the topic today is mixing, and one of the things we often hear from our customers as they begin to scale up is that they have challenges with mixing sensitivities as they start to get to the plant equipment. And mixing is often neglected until there's a problem in the plant. We usually don't hear from the customers when they're working in the laboratory about mixing. It's when they start graduating to the plant environment. The big reason is mixing does not scale. And what I'm going to talk to you about is the different tools that are being used throughout process development and eventually commercialization. So when you're in the laboratory and you're looking at your bond forming steps, the round bottom flask is typically the choice of the chemist. The Optimax system is often used as a choice for using process development. And when I say process development, we're both looking at both chemistry, also the engineering aspects of process development. And this includes the geometry of the tank that you will be scaling to. And we're going to talk about what a scale down experiment is and how we can take a piece of production equipment and use the geometry associated with that production equipment, generate a model, and then use the model's output to then give us the properties including RPM, including baffling, in something like the Optimax system, so we can then predict what's going to happen as far as success or failure in the plant environment. So the big question is, what ties all this equipment together during scale-up? So it's the models that tie all these things together. Is that you can look at a round bottom flask, you can look at the Optimax system, you can look at a production piece of equipment. What we're looking at is how to develop a model that will tell you what you're getting in the lab, or at the Optimax scale, also in the lab, will actually translate into success in the plant. And just quickly, I want to dispel some of the myths, is that RPMs scale. RPMs do not scale. RPMs are a factor that contribute to the degree of mixing that you will see in both the laboratory and the plant. Another myth is mixing can be eyeballed in the plant. And I've seen this quite frequently where somebody might look into the tank and say, it looks pretty good, it looks pretty well mixed. But what the facts are is that mixing can be modeled, and the degree of mixing can be modeled. You can use things like CFD, VisiMix. There's other models that are out there. We use VisiMix ourselves. And another fact is that each process requires sufficient insight regarding mixing parameters to obtain your desired responses. And your responses might be purity, your responses might be pH control, your response might be yield. It all depends, but using tools such as VisiMix, it'll help you predict success or failure through a series of scale-down experiments using the Optimax system is what we do, the protocol that we've adopted at Nalis. So what I wanted to be able to show you here is that what you run in the laboratory cannot be just simply scaled up using the same round bottom flask. You've got to use the proper tools, such as the Optimax system, such as the VisiMix software, to get you to that commercialization. So what we thought would be great is to give you a specific example. And in this example, we were developing a continuous process. It was for a reactive crystallization where particles were actually forming as we were dosing in and generating the product. This process was actually demonstrated using an automated laboratory reactor at the 2-liter scale, and we had success. We had great control of our particle size distribution, we had great control of our impurity profile, and then we wanted to scale this up. And we were scaling up to a 50-liter a series of two 50-liter continuous stirred tanks. What ended up happening is that with our customer was the particle size distribution failed. It resulted in these large spherical materials that we had never seen before, and we were asked to come in and model the system and figure out what happened. And so the first thing that we wanted to look at was mixing. This is an overview of the chemistry that's involved to get to the eventual product. Our desired product is at the bottom, the diamino-azoxyfurazan. It's an explosive molecule. It's being developed for the insensitive munitions program, meaning that this material, when compared to other explosives that are out there, it's less sensitive to impact, friction, electrostatic discharge, and also shock sensitivity. There's also a couple of impurities that can be formed. If the diaminofurazan is oxidized a little too far, all the way to the right we have aminonitrofurazan, and that material purges from the system. It's actually soluble in the liquors, and you'll see that material purge. So we don't see it in our isolated product, but we do see it suffering in yield. And then on the top we see the diamino azofurazan, the DAZEF. It's an impurity. If this forms, we will see it precipitate out with our desired product, and it does influence the thermal stability. We're not going to go into the details of this. There was another webinar that actually talked about the kinetics associated with this reaction. That was done last year. So if you're interested in that, please look us up and also see how the kinetics were developed for this process. Something that will be beneficial to everyone that's listening now will be to identify and go over an overview of the goals associated with the process. One of the goals from our customer was to develop a green process, and that included looking at the different reagents that we were using, the yields that we were getting, the waste streams that were being developed. There was another goal, which was developing a safe process, because this was looking for commercialization. So we didn't want to have a process that as we started to scale up, we had to worry about a hazardous process or something that could end up resulting in some kind of catastrophic incident. Another goal was to maintain particle size distribution, morphology. These factors were found to have influenced the processing and formulation of the product. There was another goal with maintaining purity. As you start to scale up, again, sometimes you run into challenges with impurities starting to grow in that you hadn't seen at the smaller scale. We wanted to make sure that did not happen. So using our models such as Dynochem, Vizimix, and the Mettler-Toledo softwares that are available, we were able to make sure that that impurity profile did scale. And the final one was it had to scale. We had to make large quantities of this material. So that was the final goal, probably the most important goal, was that this process that we developed had to scale. The webinar that we had recorded last year identified all the different challenges associated with getting the desired isolated purity of the material. Today we're going to talk more about the mixing. And mixing was one of our bigger challenges in terms of the particle size distribution, and we saw these large spherical particles that grew in over time when this reaction was taking place in the continuous process. So our focus today, I just want to point out, is going to be on mixing and using the Vizimix software. What we really like about our jobs at Nailus is that every material that we work with is unique. Every process that developed is unique. You do see some similarities, but every one of them is unique. Especially when you're looking at the difference between modeling a batch process and modeling a continuous process. You got to have people that have experience and the right tools to understand what those differences are. The number one thing with scaling up energetic materials is obviously safety. We want to make sure that everybody is safe. This might include automation, remote operations, but the process has to be safe. Going continuous is probably the safest thing you can do when you're working with energetic materials. One of those reasons is that energetics are unforgiving. If you have a process upset in pharma, typically the result is a failed batch. If you have a process upset with energetic materials, you could lose your facility or get somebody hurt. We also have challenges with in-process product. We don't want to have to isolate energetic materials when it's not needed. Using continuous process, you isolate the minimal amount of material through your production process. There's also degradation reactions that are associated with both pharma-related or energetic materials. These degradation reactions, when you're scaling up, you get into a bigger reactor and you have longer dose rates, longer dose times. You might have to have a longer hold period, for example. These degradation reactions become a bigger problem with impurity profiles and even loss of a reactor again. Heat transfer becomes a problem as you scale up. The surface area that's available on your reactor compared to the volume of the reaction mixture that you're working with, because it's not in your favor as you start to scale up. You're getting to a bigger and bigger reactor. The surface area can't maintain as you're getting to these larger reactors to be able to pull that heat out. You also have challenges with material just being out of place, and with pharma, it's not as big of a deal. With energetic materials, if you have explosives laying around on your floor, becomes a very big problem, very big challenge for maintaining safety. And then finally, ease of cleaning. We like to be able to see inside of our reactors. We like to be able to clean it free of the explosive material, make sure that it's not laying around for the next process that comes through. Very big challenge in pharma, also a very big challenge with energetic materials. One thing I do point out at the bottom here is that energetics, they are chemicals. When you look at the molecular structure of them, they have high energy. They usually have NO2 groups that are associated with them. But the engineering principles that we're applying are not limited to energetics. This is the same engineering principles that are used for all chemical processes. So here I'm pulling this, and I reference Francis Stossel, who is definitely a leader in the industry. And if you haven't read his book, I highly recommend it. It's something that we base a lot of our models and our protocols for scaling up safe reactions on. And he references a reaction that had taken place back in December 23rd, 1969, where there was an increased demand for blue jeans, and this reaction was to produce dyestuffs that were used in the blue jean manufacturing process. And the reason I like to show this is because of it's a very dramatic picture. The next slide that I show you. Here you see that a reaction has gone awry, and not only were people killed, and that there was injuries, but it devastated the community as a whole. And this is something that, as good stewards to developing chemical processes, we want to avoid. And this is another, when you're looking at batch processes and you're going to larger scale. Now, I remind you, this was not an energetic that they were making. This is something they were used in an ingredient in blue jeans, but it was also chemistry that could obviously get out of hand. And with this, I turn your focus towards continuous processing as also being a very good mechanism for having a safe operation. So the particular process that we're going to look at, the DAF process, I wanted to give you a background on it, is that we charge water to the reactor, we charge our starting material, the substrate, the diaminofurazan, we charge in a sodium bicarbonate solid to the reactor, we then charge the oxidizer, in this case it was oxone. In the batch process, there was gas generation, there was bubbling, foaming, actually took up about half the volume of the reactor. Then there was a second charge of sodium bicarbonate, which was more of a pH adjustment, because they knew that if pH wasn't within a certain range, you would form these impurities like the aminonitrofurazan that we talked about, and the DAS-EF that we talked about. Then there's a second charge of the oxidizer. Finally, you filter your solids, and you had good stuff. And the Nailist developed a nice continuous process, and we demonstrated this, as I mentioned, in the 2-liter reactor, producing about 300 grams of good high-quality material that met all the requirements in terms of particle size distribution. Here's that 300-gram process. It was a 2-liter going into a 10-liter in series. Good particle size distribution. Really had no problems with running this particular process, and isolated good quality stuff. Here's some more of the results. We have some microtrack that looks at the batch versus the continuous process. Also, take a look at the PVM images I showed there on the bottom. We have small materials, small agglomerates, and then a nice, just a microscope picture of the material as well. That's what we wanted to be able to produce to our customers as we scaled this up. So when we had designed this 50-liter process, it looked very similar to the 2-liter going into the 10-liter, where we're dosing in our oxone and DAF solutions at the same time. We had a pH feedback control loop where the sodium carbonate would be metered in to maintain a constant pH, and that fed from one reactor into the next. And what we did is we had dip tubes that would go from the 150-liter into the second 50-liter, and then from the second 50-liter into the Buchner filter. So here we were able to have a slurry being transferred with a dip tube being pumped over very, very quickly into the second reactor, and then again another pump that would be pumping over into the Buchner filter. So here we were able to isolate our solids and be able to shovel them off as needed. So here's a nice photographs of it. On the bottom left-hand side, we see our feedstocks, which is the diaminofurazan and the oxone solutions. In the center picture, we see our 2 continuous stirred tank reactors in series. And the one on the left-hand side is where we're metering the oxone and the diaminofurazan. The one on the right-hand side basically acted as a resonance chamber for that reaction to take place, but we still kept pH feedback control loops on that reactor. And then on the bottom right-hand side, you can see where the solids were isolated on a Buchner filter. And then further over to the right, you can see where our waste was being accumulated. So all the liquors that were pumped off of that filter were pumped into this blue drum that we saw. What was nice about this process is it was operated from a control room. There was minimal operator hands-on requirements. But the challenge that we ran into is that the product had an impurity that influenced the thermal stability, including the initial melt. So that required a little bit of more development, including identifying the best pH for this process. That was a separate process, and I've done a webinar that actually addresses this. So if you're interested in that, please contact me. But I also believe that it's in the archives under the Mettler-Toledo webinar series. What did come out of this particular process was big spherical material of the diamino-azoxyfurazane, the DAF material. And when you compare this to the 2-liter / 10-liter run of the continuous stir tank reactor, very different morphology, very different particle sizes. We weren't sure exactly when we first saw the pictures of this material. I remember receiving it over email thinking, what happened? And so we went to look at some models. And that the model we used was looking at Visimix. And we had to first take the geometry of these reactors that we were using, the impellers that we were using, and put them into the Visimix model. But also, we had to start thinking what could possibly be going on with this particular reaction that would have this type of dramatic change in morphology and particle size. So what we did is we thought about it. We know that when we're looking at metastable zone and we're looking at crystal growth and crystal nucleation, and we know that our product is not soluble in water, when precipitation occurs, you immediately form your product. If crystals are there, there's going to be some nucleation, there's going to be some growth. There's also going to probably be some agglomeration that might occur. All this is dictated on your degree of supersaturation in the reaction mixture. One thing that we did notice with our reactor configuration is that if there was a poor dispersion, you might lead to some of the particles staying towards the bottom of the tank. And if these particles are there and we're running this process for days, which we were, those particles can't leave the reactor. And that's just because you have a poor distribution of your solids. So we wanted to find out, is that the case? Did we have poor distribution of the solid? So just to give you an example, we show a graph here, is that when you're looking at the dispersion of the solids, if you don't have sufficient mixing, some of the particles could be towards the bottom of the tank. If you have better mixing, which we have in the middle picture here, in a dip tube, you might have better particles distribution, but still some of those solids, a percentage of them, will stay towards the bottom of the tank and have a longer residence time. And then you have the one furthest to the right, which would be ideal, where you have full suspension of your solids. We didn't know what our system looked like, so we used Visimix to try and answer that question. And that second bullet there is, what about a continuous process? When you have a batch reaction and you run, there's a finite amount of solids that are going to be generated. When you have a continuous process, well, it never ends. It could go on for a year or 2 years. So it becomes more important, or it does becomes more important what that dispersion looks like for a continuous process. Fortunately, we have a great software modeling tool in Visimix, and fortunately, we have great equipment, including the OptiMax and EasyMax and the RC1 systems, all supported by the Mettler-Toledo team. We have well-characterized equipment that we can then do scale-down experiments. And what I mean by scale-down experiments is look at your pilot scale equipment, look at your production equipment, get the geometries that are associated with these things. We can then put them into Visimix. I can then match the degrees of mixing, whatever terms you might be looking for, with the EasyMax, the RC1, and any other lab scale equipment. I can match those. I can then tell myself, when you go to an OptiMax or an RC1, use this RPM, use this type of baffling, and it matches up perfectly with your pilot scale and your production equipment. So by doing this, you're going to quickly identify any mixing challenges, because instead of running your EasyMax system at 900 RPM, you might be running at 200 RPM, because that's going to match what you're going to see in the production plant. And this last bullet is very true. It is pointless to start generating the data in the lab that's not going to be representative data that we generate in the plant. So you have to know what you're scaling to before you start doing these experiments, because of mixing sensitivity that you would not see in the lab, you will certainly see as you start to scale up. I think the biggest thing that having these tools, this combination of tools with the OptiMax and also the Visimix software, is that it gives you confidence, it helps you build confidence in your process. You can see firsthand of the equipment that you're going to using Visimix, what those mixing parameters are, and you can replicate them using scale-down experiments in something like the OptiMax system. That's going to tell you whether or not your process is going to succeed or fail, and that's what we did with this particular crystallization. So I wanted to give you sort of a set of figures here so you can understand what we were doing. Is we were trying to figure out what levers we had to play with at the 50-liter scale with our continuous process. And by doing that, we looked at the impeller configuration and the RPMs that were being used in the 50-liter scale. We then took that information and we fed it into VisiMix. We then did scale-down experiments using the Mettler-Toledo systems, and then from that, we tried to predict failure and predict success as we started to scale this up. We then took that information and carried it forward into production, and then the output was success. And so we'll go through all those details one at a time. So I'm not going to go through these definitions in detail, but they're here for you to come back and refer to as well. But there are certain things, there's many variables that VisiMix can predict. These are some of the ones that we thought were going to be very beneficial for us. The maximum degree of non-uniformity, you can kind of think of it as how many solids are at the bottom of the tank versus how many solids are at the top of the tank. And that's what we definitely wanted to know. What did our distribution, what did our dispersion look like as far as the solids in this tank? The average concentration of solid phase in the continuous flow, you would know what, if you had the solids suspended, ideally what that ideal value would be. We wanted to see how close we were to ideality. And then the relative resonance time of the solid phase is how long did that particle stay in your reactor. If it stays in too long, that might be one of the challenges that you have with growing, is it's growth dominating and getting that spherical material. So I put together some tables that are going to look at how we change RPM, and these are all VisiMix outputs. How we look at the turbulence parameters and the solid liquid mixing parameters. These are just a few. There's a lot more that are out there, but these are just a few. And I just want to show you some of the changes that you'll see just by simply changing RPM in the existing system. So we haven't changed the impellers yet. We're just looking at the RPM. And you can see things like the energy dissipation, the maximum value for that, going from the 150 RPMs, which is what the reaction was run at initially, going to 230 RPMs, dramatic changes in energy dissipation maximum value. The average value also, dramatic changes. Characteristic time of micromixing, dramatic changes. Remember, this is a pH feedback control loop that we're looking. Micromixing is very important to this process. And then the solid liquid mixing parameters. The one that I have highlighted here is the average concentration of the solid phase in continuous flow. We went from 4.44 to 6.31 when ideality is actually at 8. And so that just showing you just a simple increase in RPM is dramatically changing these mixing parameters. So that's definitely one of the parameters we're going to be examining as we go forward. So based on the previous slide, we know that the higher RPMs definitely is leading us towards a more desirable process. Now we look at the impellers that have been selected. And when you start to scale up, and you've seen these half-moon type impellers that are used in the laboratory, and sometimes manufacturers of the larger scale equipment also use these half-moon type impellers. What we wanted to do now was, let's compare that half-moon impeller to something like a pitch blade impeller, 45-degree pitch blade impeller. Not only the single pitch blade impeller, but also let's look at a dual pitch blade impeller as well. Now you start looking at the same VisiMix output, and you start looking at things like the average concentration of solid phase and continuous flow, which is in that second row. We go from 6.32 with that half-moon impeller, and to the dual pitch blade impeller is 6.86. Again, another dramatic increase. The relative resonance time, we go from 1.27 to 1.17. We're heading in the right direction. We're going down. And then that characteristic time of micromixing of 4.63 down to 2.79. That's much better for our pH control. Now that top row, the maximum degree of non-uniformity, I save that one for last because it's going to be a lead into my next slide, is that you see that you want this to be a low number. You want this percentage to be low. And so being at 35% and then I jump to 97%, that doesn't make a whole lot of sense to us until we start looking at some of the figures that VisiMix generates for us. Because initially you think, well, you're going in the wrong direction. So let's look at that slide. When you look at the slide, you can see that the dual impeller, the second impeller, is actually interfering with the flow of the solids. So that mixing flow pattern gives you a higher degree of non-uniformity. But if you look at the two plots that I've shown here, is that if you have just the single impeller, you have a 39% maximum degree of non-uniformity. But when you look at the actual distribution of the solid phase on the second graph there, you can see that I have a local high degree of non-uniformity because it's banging, the particles are banging into that that second impeller and the flow patterns being disrupted. But overall, I have a much better degree of non-uniformity above that second impeller. So that's the one we actually stuck with. So now the challenge is you've got your model, you have your 2 liter to 10 liter set up, and we've shown and demonstrated that that's what we want. We have the initial 50 liter set up. We've now modeled that process, and we've determined that the dispersion was poor. We've now revised our 50 liter setup, and at this point you're relying heavily on your models. It's very expensive to get into the plant. It's very expensive labor to run these, so you have to be have a high level of confidence to be able to take this process forward. And we did. We thought that the models that we used, the scale down experiments that we had done using the Mettler-Toledo tools, all this led us to believe we've identified the problem, we've mitigated the problem, we've made changes to the 50 liter setup. So now we've gone from the half moon impeller to the pitch blade impellers. We went to a dual setup, and we also increased our RPM from 150 RPMs to 230 RPMs. We would have gone higher if we could have, but the equipment had limitations, so we stopped at the 230 RPMs. And the comparison is great. We can see that when we start off, the morphology and particle size, just from the photograph here, looks very consistent with with the 50 liter setup. The revised 50 liter setup looks very comparable to the 2 liter setup, and looks nothing like the initial 50 liter setup. So we were very happy. Another thing I wanted to point out here is that when you're using dip tubes, if you don't have good dispersion, you can always lower that dip tube to try and get to the more dispersed materials, but that's not something we had to rely on with this particular project. Now we're going to go over a subject that's near and dear to everyone's hearts, is cost avoidance. And just to give you some estimates on this particular project, is that the labor costs were around $60,000 for the processing, drying, and packaging. The material costs alone were about $50,000. And I've worked in pharma, and I know that a lot of the ingredients can cost a heck of a lot more than just that. Some of them are 10 times more, or even larger. The analytical support was about $35,000. So for one step, we're looking at about $145,000. Now that's one step. Now typically, in pharma, you usually have 5, 6, 10 steps. So you could be as much as about $1.5 million that's going into it. Well, this modeling effort, this particular one, costs about $30,000. So we were able to model the reactors, the process, do the scale down experiments, do the analytical, provide the customer a report, and it took about a total of about 2 weeks time. So $30,000 versus $1.5 million, I think the answer is pretty clear, is that the modeling effort is definitely pays for itself. So now we're getting towards the end, and I really appreciate everybody hanging in there with us. I have a couple of slides on scale-up thoughts, and it's the same story as with anything in life, is that you have to have the right combination of the tools that you're going to be using to attack whatever challenge you have. Also have the right combination of experience, the right team put together to tackle these challenges. We all know that producing chemistry is a challenge all by itself. And oftentimes in pharma, your targets can have a large amount of steps to get through a phase 1 and phase 2 effort. Typically a lot more steps in phase 1, and hopefully you've done some process development and some great chemistry to whittle those steps down into phase 2. But modeling is your friend as you're going through these challenges. It allows the user to quickly and efficiently evaluate how that process is going to run as you start going to a pilot scale, or even a kilo lab, and then to the pilot scale, and finally to the manufacturing. The automated lab reactors, including OptiMax, it gives you the proper tool to get the data that you need for building your kinetic model, for evaluating mixing. And without these tools, you're not able to do scale up properly or efficiently these days. And this slide, I've got the picture of the material with the large spherical diaminoxoxyfurazan, and compared it to what we eventually achieved in the 50 liter continuous process. Is that you don't want to be the guy that comes back and shows your boss the picture of these large spheres. You want to be the one that says, I predicted that you could get these large spheres if you didn't have adequate mixing, but this is what we were going to get with the proper RPM, the proper impeller type, the proper degree of mixing, because we modeled it and we reduced overall risk. It is absolutely the fastest possible path to market, is by using these modeling tools. And that last bullet, say it all the time, chemical engineering is not magic. It's a science. And so when people say it's an art and they're trying to scale up and we know how to do it because it's an art, I don't believe in it. I believe in using the models and using the proper tools and sound chemical engineering principles. That's what's going to get you to scale. Well, we've come to the end of this webinar, and we have a nice summary slide with a few bullets that I wanted to conclude with. First bullet is VisiMix allows for quick and efficient investigations related to mixing that minimizes risk upon scale up. Couldn't be more true. You actually have a tool that you can use to model your customers' pieces of equipment that they're actually going to, whether it's a contract manufacturer or it's a piece of equipment that's in their existing plant. You now have a tool that you can model and then come back into your own laboratory using these synthesis workstations such as EasyMax or OptiMax or even your RC1. You can use these tools, these combinations of automation and modeling to define a scale down experiment and determine whether or not you're going to have a challenge as you start to scale up, in particular with mixing. VisiMix also allowed us to evaluate a specific reactor configuration. In our case, this was the 50-liter reactor that we had with our particular customer. We were able to even model it in a continuous flow operation. So something that everybody's always trying to do is save money looking at continuous operations. VisiMix allows you to be able to do that. And in the end, we were able to produce a high-quality material for our customer. Our new focus now is looking at the starting material, the diaminofurazan, which we've done quite a bit of work on already, and I'm hoping to share a webinar with you in the next 6 months to a year discussing that project, another continuous process. Also the optimization of the equipment trains for commercial manufacture of the product DAF. Right now what we've done is the pilot scale. We basically looked at, hey, you need to make 20 pounds of material. We did it efficiently, we did it safely. What happens if you want to commercialize this? We can use everything we've already learned using VisiMix. We've also done a lot of work with DynoChem in terms of kinetic modeling. We can put these together, use this suite of technologies to put together a commercial process. So the last two bullets will definitely hit home, and having and knowing how to use the right tools makes all the difference between success and failure. So it's not just having the tools, it's knowing, it's having the experience with the tools, it's having the right team put together to get the analytics, to get the chemistry, to get the chemical engineering. All these things put together is what's going to produce a lot of success with your company and also with your customers. And finally, that last bullet, modeling is proven to save development time and money. We all want to save money. The economy probably couldn't get any worse out there for a lot of companies at this point. So us being able to share our knowledge and to share our experiences in these tools is going to definitely save you money if you apply them properly. So we'd love to hear from you. Please give us a call in regards to this webinar, future work, future collaborations. And I want to thank Mettler Toledo, and I want to thank VisiMix very much for allowing us to have the resources to continue to do our work. Thank you very much. And at this time, I'll entertain any questions.